Good evening, everybody. Great to see all of this wonderful biotech happening in Santa Cruz. I want to tell you a little bit about our company, Somagenics. Our focus is RNA. We use RNA molecules as drugs to target RNA. And I'm going to spend our limited time here telling you about, sorry for the unappealing picture, but many of you may know people that are suffering from diabetic foot ulcers. Diabetes is an epidemic, of course, and 1 in 4 diabetics will develop a foot ulcer, and many of those will lead to amputations and shortened lifespan, and this is a tremendously costly problem. And we're addressing this by looking at the one of the main biochemical defects that happens in diabetics. So the central player there in blue is HIF1 alpha, which is a protein that's a major regulator of wound healing. And the green factors on the right are things that are kick-started by HIF1 alpha when a wound needs repairing. And those green factors then promote angiogenesis and move skin cells to the site of wounds and promote the healing process. Normally this is turned down because it's not needed, and it's turned down by this red protein PHD2 blocking HIF1 alpha. In diabetics, the turn-on, which is to amplify HIF1 alpha, doesn't work. And so our approach is to inhibit the inhibitor by using an RNA that targets PHD2. And our therapeutic modality we call synthetic small hairpin RNA, or shRNA. It's just like it sounds, a small hairpin of RNA that can bind to a protein called AGO2, get processed in such a way that it then binds a target RNA and processes that in a way that destroys its ability to function. We deliver this to the wound by applying it in layers, alternating negatively charged RNA with positively charged polymers that are biodegradable. We coat that on a bandage material, like Tegaderm. And this technology came out of our collaborator, Paul Hammond at MIT. When you take this material then and lay it in a wound bed, it biodegrades over a period of a few days. And particles come off that can be taken up by cells at just the right size and charge to do that. And so if we take, for example, some of this mesh, it's coated, cut it into a size that can fit just over the wound bed, and then in this mouse model we've used in collaboration with partners at Stanford. Small punch wounds on the mouse. This is a diabetic mouse, which is why it's fat. And then these are laid into the wound bed, and then we measure how much faster the wound closes in the presence of this treatment. And here's some of the data. You can see that the controls are on the left, and the active molecules, including combinations, are on the right. And we get a very significant improvement in speed of wound healing. Our one other therapeutic program is on hepatitis delta virus, which is not commonly known, but it's actually the most serious form of viral hepatitis. And it's something that people already infected with hepatitis B are prone to. They can get super infected, and it causes a great deal of suffering, mostly in other parts of the world, but it's also prevalent here. There's no vaccine, no specific treatment, and we have an RNA-based program that's addressing that. And then finally, I want to just mention that another side of our company has focused on developing RNA detection platforms, and we're very proud to have invented, in this case, an RNA sequencing technology for making libraries of small RNAs that are better than anything else out there, and that's now been spun out into another company called Get Biotech that's run by my colleague Sergio Barbaran there in the middle. So this is our team, and we're very happy to be down the other end of Delaware Avenue, and thank you for listening.
Thank you.